Hello friends. In today's lecture, we will look at a few miscellaneous points that we were supposed to discuss as part of description of boundary layers. First, we will talk about a couple of definitions of boundary layer thickness, which have commonly been used in the boundary layer literature. And then what we can do is to discuss about what happens on a flat plate boundary layer when the flow starts flowing over it, because the Reynolds number is a function of x. So as x increases, as we go from the leading edge downstream, the Reynolds number goes on increasing, and at some particular point, the Reynolds number becomes critical. That is the Reynolds number beyond which the flow cannot remain laminar. So using because of that, the flow starts becoming unstable and therefore transitions to turbulence. And then if you look at further downstream, there is a certain region where this transition of the flow from laminar to turbulent, and beyond that there is turbulent flow. So if I have to calculate the wall shear stress or the heat transfer from such a flat plate boundary layer, then how do we go about doing that? We should have studied this as part of your undergraduate as well as your advanced heat transfer course, but we'll just quickly run through that. So these are certain points which, for the sake of completeness and for the sake of clarity of understanding, we will discuss today. Okay. So today's lecture is primarily devoted to a few miscellaneous points which we are supposed to discuss as part of boundary layer theory. So the first thing that I will talk about today, so let's move on to the whiteboard so that we understand that. The first thing we'll talk about is definitions of boundary layer thickness. So all of us understand this delta is the distance from the flat plate, or for that matter any solid surface. We have discussed so far only flat plate, so it's a flat plate, but otherwise any solid surface at which the velocity attains 99% of free stream velocity. That is u by u infinity is equal to 0.99 at y is equal to delta. Okay, so this is one definition that we have been using. Okay, so some textbooks therefore refer to this delta as delta 99, although for all practical purposes we say that this is the edge of the boundary layer beyond which we can take the u to be equal to u infinity. Okay, but in real terms as well as in mathematical terms, delta attains u infinity, u attains u infinity asymptotically, and therefore strictly speaking 100% u infinity is attained only at y is equal to infinity. Okay, but for all practical purposes we normally treat delta 99 as the thickness of the boundary layer. So this is something that we are already familiar with, but in addition to this we define two other thicknesses. One is called the displacement thickness, we can denote that by a symbol called delta star, and we have another quantity which is called the momentum thickness. which is called theta. So these are quantities defined so that it becomes quite straightforward to evaluate these quantities, because delta 99 is actually a quantity which can be determined only when if I know the analytical function, or I fit a curve to the solution and then obtain the location at which the velocity crosses 0.99 or non-dimensional velocity crosses 0.99. Whereas these two are definitions which can enable us to mathematically evaluate boundary layer thickness or its representative in some form. That's why we define them in this way. Let's understand what each of these means. So first let us look at delta star. So delta star is called displacement thickness, as you can see it. This is, you can define it as the distance by which the boundary layer is apparently displaced because of the presence of the free stream is apparently displaced because of the presence of the solid surface. What does it mean? Suppose you consider free stream as the one which has velocity equal to u infinity. Then the mass flow rate per unit delta y can be given as let us say rho u infinity dy. Okay, this is so suppose this is the suppose this is my flat plate, and this is the free stream that is coming, which is at u infinity. Then there is a certain decrease in velocity as you approach the wall. Okay, so if I draw a line up to which if u infinity prevailed, then the mass flow rate that is going through that region is the same as the mass flow rate that goes through the boundary layer. So apparently, because of the presence of this plate, the boundary layer displaces the free stream by this distance delta star. That is, if I say integral from 0 to infinity of rho u dy, which is the mass flow rate through the boundary layer with u as a function of y, is equal to the integral from delta star to infinity of rho u infinity dy. Since we are dealing with constant density flows here, the rho can be removed. So the integral from 0 to infinity of u dy is the same as the integral from delta star to infinity of u infinity dy. Or in other words, I can say that this is the extent to which, so in this region, the integral from 0 to infinity of u infinity minus u into dy. So this is the defect of velocity, so this small amount. This is the extent by which this has been displaced. So that should be equal to u infinity times delta star. Okay. So u infinity times delta star is the amount of mass flow that would have gone through this region if the velocity had remained u infinity all the way up to the plate. Now, since the velocity is decreasing from u infinity in this region, so if I say 0 to infinity, or this could also be 0 to delta in that sense, but we'll just write it as u infinity. So this is a definition of delta star that you would get. If I take this u infinity down here, then I'll get this u infinity goes here because it's a constant that can be taken. Then it becomes equal to integral of 1 minus u by u infinity dy from y is equal to 0 to infinity. Okay, so this is the definition of delta star. So basically, what does delta star say? Delta star is the distance by which the boundary layer is apparent, so the free stream is apparently displaced because of the presence of the boundary, the wall, solid wall. That is, whatever mass defect happens because of the decrease in velocity due to the presence of the solid wall is accounted for using a distance delta star by which the boundary layer has been displaced, apparently displaced, so that the same mass flow rate of the free stream can be taken. Okay, so that is the way we define displacement thickness. So you can define the momentum thickness exactly in the same fashion. Now, instead of looking at mass flow rate, we look at the momentum. So momentum thickness theta is the distance by which the boundary layer is apparently displaced so as to carry the same amount of momentum as it is in the boundary layer flow, but with only free stream velocity. So since the mass flow rate is rho u dy, and if it is carrying the velocity at free stream velocity, it's carrying momentum at free stream velocity, this multiplied by u infinity. This integrated from theta to infinity should be equal to the integral of rho u squared dy, that is rho u dy multiplied by u itself, from 0 to infinity. So this is your primary definition, or we can actually define as the momentum defect, which will be integral from 0 to infinity of rho u and multiplied by u infinity minus u dy. Now the rho can be cancelled out in both of these, so you can just remove without rho here. This should be equal to u infinity square into theta is a thing that you define. So if you take the u infinity down here, theta will be defined as integral from 0 to infinity of u by u infinity multiplied by 1 minus u by u infinity. Okay, so this is the definition of momentum thickness. So this is basically the thickness or the distance by which the boundary layer is displaced, the free stream is displaced if it were to carry the same amount of momentum as the case of the boundary layer flow. So these two are the thicknesses. So you have the wall, and theta is the distance by which you displace the boundary layer, so that the boundary layer with velocity u infinity coming up to the thickness theta would have the same momentum, which is rho u. So this momentum is the same as the amount of momentum that is carried by the entire boundary layer. That is, so that is the thing that you do. So that is this definition. Okay. Now, if you look at this, you can recognize that this looks quite similar to the left hand side of your momentum integral equation. So for flat plate boundary layer, the momentum integral equation looks like d by dx integral from 0 to infinity, or 0 to delta s, of u infinity into u minus u multiplied by u infinity minus u. U times u infinity minus u dy, and this we write it as equal to tau wall by rho. Right? This is what we get because we integrate the left hand side, we get this. Right hand side, there is only one term, del square u by del y square. You integrate that between 0 to infinity. At infinity, tau is 0. At 0, it is this. So you write this as this. So this is your expression. So what this happens is, if I divide throughout by u infinity on both sides, u infinity square, then on the right hand side you have Cf by 2. Okay, and on the left hand side you have d theta by dx. So d theta by dx is equal to Cf by 2 is the momentum integral equation for the flat plate boundary layer as we have derived earlier. So this theta is a familiar quantity, and therefore your theta expression at any given location you can find out using this. The relationship for theta will be having similar constants as you had in the CF term. So that is basically what we understand. So let's look at the case of flat plate boundary layer. Okay, so for a flat plate boundary layer, you can define the quantities delta by x, delta star by x, and theta by x, which are the non-dimensional thicknesses for laminar flow and for turbulent flow in terms of Reynolds number and Prandtl number. This is something that we have derived in some form or the other. I'm just going to summarize them here. And actually, if you perform the integrals that are given in the question, in the definitions, then you would get the same expressions. So from for laminar flow, from the similarity solutions, you get this delta by x as 4.92 into Rex raised to the power of minus half. And from the 1/7 power law, the turbulent boundary layer actually does not have an analytical profile. It has only experimental data fitted. So you can use different turbulent boundary layer profiles and you will get different constants. I'm writing it for the 1/7 power law. Okay. So this is not an analytical solution, but this is reasonably close to. This is an analytical solution. So here this will be 0.37 into Rex to the power minus half. Okay, so this is the number that you would get. The number would vary slightly from one to the other. For delta star, you get a 1.73 into Rex to the power of minus half. So at any given x, this is the displacement thickness, and the momentum thickness would go to 0.038 Rex power of minus half, and this will be 0.664, the constant you are familiar with, Rex the power of minus half, because that is the expression that you get in the CF by 2, and here you get 0.0296. Sorry, this is Rex to the power of minus 1 by 5. Sorry about that. So these are the turbulent boundary layer and these are laminar boundary layer results if the boundary layers were turbulent all the way from x is equal to 0 in this case. Okay, so this is laminar and this is turbulent boundary layer, the thicknesses that we have there. So you can see that this and this have the same constants as in the case of CF by 2 for the flat plate boundary layer. That is because of the relationship of the theta to the CF by 2 in the momentum integral equation. Okay. So that is one point that I wanted to convey regarding the definitions of different kinds of thicknesses. So you can see that this delta star and theta do not involve that 99% business, but it's actually an integral all the way up to the free stream, and therefore you can actually derive that the moment any velocity profile is analytically given, or even assumed cubic or quadratic or half sine profiles that you do, then from that you can do the integral. Okay. The integral can also be written, the upper limit of the integral can also be written as delta notionally, but the delta is understood to be where the velocity reaches the free stream velocity. So that's why we write infinity in these definitions. Okay. So then we move on to the next concept that I wanted to introduce today, which is overall skin friction. Or wall shear. or heat transfer. So all the expressions that we have derived so far are CFX and NUX or STX are local quantities. What do I mean by local quantities? So suppose I have a boundary layer, I have a flat plate, and this is the X coordinate. At any given X, there is a certain REX, and as a function of that REX, you define CFX, you define NUX, you define STX. So this value is CFX at this location. That is, if I write tau wall at X divided by rho U infinity square, this will be CF at X divided by 2. So this is the way it is defined. Similarly, Nusselt number is basically defined as this is H at any X into X by K, and that is equal to NUX, and this is written as a function of REX and PR. Okay, so this is how we have written that. Now this H of X is basically the heat transfer coefficient locally such that the heat flux at any X is equal to H at X into T wall minus T. Okay, so this is the heat flux at that location, which is defined as the local H multiplied by 2. So this H is at this location, and similarly this CF is at this location at any X. Okay. But quite frequently what we would need is the overall quantity. So suppose I have a plate of length L, then I would actually need the integral of the shear stress multiplied by the area, which is the shear force over this entire plate, or the averaged quantity, which is the shear force over the entire plate divided by the area of the plate. Similarly, the heat transfer over the entire plate divided by the area of the plate. So you need an average heat transfer coefficient or average skin friction coefficient as an output of most of our convective heat transfer problems. Now, it is straightforward so long as you have the same expression throughout the plate as we have been discussing. We have been discussing the laminar case where everywhere the flow is laminar and therefore the same expression holds for skin friction in the entire plate, or the same expression holds good for heat transfer coefficient or the Nusselt number for the whole plate. But that is not the case in most real life problems. So what happens is that as X increases, the Reynolds number REX also increases, and at a certain REX the flow cannot remain, after a certain REX the flow cannot remain laminar, and therefore it transitions to turbulence because of the instabilities overpowering the viscous forces that are trying to contain them, and therefore the flow remains laminar until a certain distance called RE critical. Okay, and beyond that this flow gets disturbed and then it becomes fully turbulent. So you have a laminar region, you have a transition region, and you have a turbulent region. Okay, so what we commonly do is to extend the laminar region and extend the turbulent region backwards and say this is the point of critical Reynolds number up to which the laminar expression will be valid, beyond which the turbulent expression will be valid, as if the turbulent transition happened instantly, which is a convenient way of doing things. But in reality what actually happens is this region of transition sees that some part of the plate the flow is still laminar, and there are some parts in which the disturbances start happening and there are eddies that start getting shed. So there is what is called intermittency. What do you mean by intermittency? The flow is intermittently laminar and intermittently turbulent. The laminar fraction is higher closer to this end and the turbulent fraction is higher closer to this end. So the intermittency goes on increasing, and we get fully turbulent flow after a certain point. So in the transition region, it is very difficult to quantify things, and it's also dependent a lot on the local conditions. That is, if the plate is rough or if there is any geometric imperfection. So you never can make a very perfectly smooth plate for any experiment. So whenever there is a plate, it always has some level of roughness depending on the process by which the plate was actually manufactured. So you can have this, if you look at it microscopically, there would be this kind of a structure, and there would be some things which are bigger than the others. So those bigger ones are the ones which introduce the larger disturbances and therefore lead to transition earlier. In the region where the flow is laminar, these disturbances are controlled because the viscosity overpowers the disturbances and the flow becomes smooth again. But in the transition region, in some places it is able to control, in some places it is not able to control, and in the turbulent region, nowhere any of the disturbances can be controlled by the viscosity, and therefore the flow becomes completely turbulent. So this is basically what actually happens. So in such a case, if you look at the boundary layer profiles, you have to have a certain region. So this you call it as REX critical. For a flat plate boundary layer, this value is assigned to 5 into 10 to the power of 5. So if the Reynolds number is lower than 5 into 10 to the power of 5, we use the laminar expressions, and if the Reynolds number is higher than 5 into 10 to the power of 5, we use turbulent expression. So if I say for X less than X critical, what is X critical? If REX critical is 5 into 10 to the power of 5, which is equal to U infinity into X critical divided by U, where X critical is this distance from left end to the point where the Reynolds number reaches 5 into 10 to the power of 5. Then this X critical can be evaluated by this X critical is equal to REX critical into mu by U infinity. Okay, for the given case where the U and U infinity are known, you can calculate the X critical. So for X less than X critical, flow is laminar, and X greater than X critical, turbulent. In which case, if I want to calculate, for example, tau, so the average tau wall multiplied by the area of the plate up to any X, let's say some value of X greater than X critical. So X less than X critical, of course, it's only the laminar flow expression that will be valid. But if I have a location which is on this, or the X critical X is equal to L, which is the end of the plate, at for all X greater than X critical, the average tau wall from the leading edge up to that X. So tau wall bar of X multiplied by the area of the plate. If I take the plate to be unit depth as in the plane perpendicular to the paper, then this area is equal to 1 multiplied by X, which is X. This is equal to integral from 0 to X critical of tau wall laminar dx. Again, dx is unit width and dx, so this is the area, and plus from X critical to X, it is tau wall turbulent to dx. Okay, and tau wall laminar and tau wall turbulent can be written in terms of this one, because tau wall is Cf by 2 into rho U infinity square. Okay. So we can actually divide throughout by rho U infinity square. So if I divide by rho U infinity square divided by rho U infinity square divided by rho U infinity square, and we can also put a half here so that you don't have the Cf by 2 but you get Cf. Then you get on the left hand side it will be X times Cf bar at any X. So this is the average skin friction coefficient for the region between x is equal to 0 and any x which is greater than the critical x. This will be equal to integral from 0 to x critical CF laminar dx plus from integral from x critical to x of CF turbulent. Okay, so now if you can look at the expression for this CF laminar at any x, CF of x which is laminar, this is given by 0.664 into REX to the power of minus half, and CF x turbulent is equal to 0.0296 into REX to the power of minus 1 by 5. Now, what is this REX? This REX is nothing but u infinity into x by nu. So in this case, x is the only variable which has to be integrated. The u infinity by nu will be a constant that would come out. So basically, what you will get is x CF bar of x would actually be equal to integral from 0 to x critical of okay, so I can take the constants out and then write it a priori. So then I'll be able to write 0.664. This is RE to the power of minus half. So you will get a nu by u infinity to the power of half integral from 0 to x critical of dx divided by x to the power of half. So this is the first part of it. Plus similarly, you will get a 0.0296 into nu by u infinity raised to the power of 1 by 5 multiplied by integral from x critical to x of dx divided by x to the power of 1 by 5. Okay, so you have the laminar part of it and the turbulent part of it. Now this is the function of x that needs to be integrated. This is from 0 to x critical and this is from x critical to x. So this is how you can do the integration and find out the value of CF average at any x. Okay, so there is an x here also. There would also be a function x here. So it would be a function of x in some form, and that can be evaluated. Okay, so that is the way you evaluate the average shear stress. So the average shear stress then calculated. Once I know the CF bar, the average shear stress would be nothing but tau wall divided by half rho infinity squared. So you multiply it by half rho u infinity squared, you get the average shear stress over this region, and multiplied by the area, which is x into 1, then you get the average shear force over the surface. Okay, so that is your expression that you need. Similarly, for heat transfer, average heat transfer or average heat flux. So you have q dot of x at any location. So if you want to find out the average, then you need to integrate this into dA, which will be 1 into dx from 0 to x, and this is the total heat transfer. This divided by the area will be 1 over x, right? Because the area is x multiplied by 1. So this is the average heat flux, which you can write as q dot double prime bar at any x, and this will be equal to h bar of x into T wall minus T infinity. And this itself will be equal to h of x into T wall minus T infinity. So the T wall minus T infinity can cancel out on both sides. So what you can get is h bar of x, and I can bring this x to the other side into x is equal to integral from 0 to x of h of x dx. So you can see that when you try to integrate the heat flux, it actually is an integral of h and not the Nusselt number. That's the thing that we need to be careful about, because the nux also contains another x, which is h of x into x by k. So the h of x would actually be equal to nu x into k by x. Okay, so it contains another x that's here. So you cannot integrate the nu, but you need to integrate nu by x into k. That's the expression that you get. This is your expression. So this, if I write it for x greater than x critical, then this will become integral from 0 to x critical of h laminar of x dx plus integral from x critical to x of h turbulent of x. So this is how the integration gets performed. So if, for example, the Nusselt number at x is 0.332 Rex to the power of half PR to the power of 1 by 3, then your h of x would actually be equal to 0.332 into PR to the power of 1 by 3 into u infinity x by nu. So u infinity by nu to the power of half into x to the power of half. Now this is going to be equal to into k by x, k by x. So this x to the power of half becomes x to the power of half here. Okay, so this is the expression that you get. So all of this remains a constant, and x to the power of half goes here, so it will become this constant multiplied by dx by x to the power of half in this expression. So this is for laminar flow. And similarly for turbulent flow, if I have an expression which is again in terms of 0.0296, then it will take that expression here. So it's the x to the power of 1 by 5, x to the power of 4 by 5 divided by x will get, you will get x to the power of minus 1 by 5 again. So that is dx to the power, dx divided by x to the power of 1 by 5 will get integrated exactly in the same way as we saw in this expression. Okay, so that is how you calculate the average heat transfer coefficient. And once I have the average heat transfer coefficient, I can calculate the average heat flux at any x as h bar multiplied by T wall minus T infinity. Okay, and the total heat transfer would be equal to Q dot up to any x. This will be equal to x times Q dot double prime. Okay, which will be equal to h bar x into T wall minus T. Okay, so that is how we evaluate the overall heat transfer and overall shear stress. So it's a straightforward thing, but I thought that it's important to explicitly state all of this in order to avoid any casual errors resulting out of directly trying to integrate CF on one side and NU on the other side. In CF integration comes out to be correct, whereas the NU integration comes out to be wrong because there is a dependence of 1 by x between h and NU. So there is that that needs to be taken into account. Okay. So I'll stop this lecture here. These are the miscellaneous points that basically I wanted to convey to the class. I'll stop this lecture here, and in the next lecture I will spend 1 hour on understanding of how turbulent flows can be computationally calculated. So when you want to use the ANSYS Fluent software for solving the turbulent boundary layer, then what are the things that normally are done, and what kinds of models are there available for you to choose from, and what are the plus and minus of each of those models, and a little bit of introduction to how that model is implemented will be the content of the next lecture. Okay. So with that, I will stop this lecture. Thank you.